Okay, so here is an example of that I found via online. You're given a position versus time graph for a simple harmonic motion, SHM. All right, so there are 6 different questions that it wants you to find. I will help you find each one at a time. All right, let's go ahead and find or question 10 and 11 here. Question 10 asks us to find the angular frequency, which is omega. And in this case, to find number 10, you have to know that angular frequency, by definition, is angular displacement divided by the change in time. And from this graph, I can pick 2 identical points. I would choose to pick the top point here at 2 centimeters, and I will go all the way over to the next peak, which is a full cycle. And in a full cycle in physics or math is 2 pi rad. And therefore, if I go down on the time, that is 4 seconds. So really in this graph, it's pretty easy to extract. I can pick any 2 identical points on this particular function. So I've chosen to pick 2 identical peak to peak. That is 1 full cycle. 1 full cycle is 2 pi rad. And therefore, that time for that event to occur is 4 seconds according to the graph. So I just plug and chug. Okay. So angular displacement would just be 2 pi rad divided by 4 seconds. And because the question asks us for angular frequency in rad per second, we are pretty much done. If you do the calculator work, you should get 1.57 rad per second. And that is answer choice D. All right, 11 asks us to find the maximum speed in centimeters per second. To find V max, you have to know this function. V max is simply the amplitude of the spring oscillation times the angular frequency. In this case, we know both values from the graph. We can extract that A is 2 centimeters, and omega we just found in part A, and it wants it in centimeters per second, so we do not have to convert centimeters to meters in this particular diagram. All right, so plug in A is equal to 2 centimeters, omega is 1.57 rad per second, and then if you do that, you get 3.14 centimeters per second. All right, that matches with choice E, and then let's move on to 12. I think 12 and 13 are the hard parts in this particular example. For 12, it says to find the velocity at 1.7 seconds. All right, but to do so, you need to know this function V of t is equal to negative a omega sine t omega t for this particular problem. It's because you're given a cosine graph here. So if you're familiar with SHM, this is starting at 2 centimeters at times equal to 0. Indicates that it's being stretched to the right a distance of 2 centimeters before the mass is let go and it's free to oscillate. Because it's stretched to the right, it implies that this is a cosine function. And from calculus proofs, the velocity function is the first derivative of the x of t. So in this case, the derivative of cosine is negative sign. That implies the negative sign in the front. And then this is why your velocity function is a sine graph. Okay. So if you don't know where this function comes from, dig around a little bit and then, or just take it for what it is for this particular problem. All right. And then from here, we know that A is equal to 2 centimeters from the graph. And then we know omega, which is calculated in question quote unquote 10. And then here we notice that we have sine of omega t, and omega is 1.57 rad per second times time, which is 1.7 seconds. But I do want to point out here, this is usually where folks who are newer will go wrong. They just like to plug in chug values without paying attention to what unit needs to be. Here, your omega is in your omega has a unit of rad per second, but you're taking sine function here. So this needs to be changed out to degrees per second, okay? So let's do conversion real quick. You need to convert 1.57 rad into degrees, and the conversion is for every 2 pi rad, which is 1 revolution, 1 cycle, and that is just a circle, and there are 360 degrees in a cycle. And if you do that conversion correctly, you should get about 89.95 degrees for this particular problem, okay? All right, so now we have to use this 89.95 degrees. Otherwise, again, you'll get play and you won't get any answers at all. So it's important to pay attention to units as you practice these types of problems. All right, so I just carry everything down. And so instead of 1.57 rad per second, I have changed it to 89.95 degrees per second. And the time remains the same. Units cancels out. And if you do that, you should get a velocity of negative 1.43 centimeters per second, which choice B. All right, let's do 13. 13 asks you, at what time is the position half of the amplitude? So because it asks for position, we would just bust out the position function. Again, for this particular graph, whether sine or cosine depends on what's given to you to start. You have to recognize for this function here, it starts at an amplitude of 2 centimeters to the right, which indicates that it is a cosine graph. So here we have A is equal to cosine omega t based on the graph, and then we know A, and we know omega, and then we know x because it says that x is half of A. So we can just plug stuff in. It says when position is half of the amplitude, therefore x of t would just be the amplitude divided by 2. And that's where the substitution comes in. And then again, here you have to pay attention to omega because there's a cosine function in the front or operation. You have to make sure you convert omega from rad per second to degrees per second. And you notice here, I know everything. I know A, and then the only thing missing is T. But really, even if you know A, you can just cross it out because it appears on both sides. So I can just go ahead and cross out A. So if you want, you can plug in 2 centimeters, or you can just mentally cross it out because there's an A on the left side and there's an A on the right side. And for this particular step, you can cross that out. So if you cancel out A on both sides, the left side remains just 1/2. And then I took out the A there. And you notice here, the only thing missing is time, which is pretty light work. So therefore, the first algebraic step to do here is the inverse cosine. So make sure you do your algebra carefully. To get rid of cosine, you do inverse cosine on both sides. That'll leave us with cosine to the -1 of 1/2. And then here it's just 89.95 degrees per second. So if you do your calculator work correctly, you should get a time of 0.667 seconds, which match choice A. Okay. All right. So here's question 14. 14 asks us if the graph represents a pendulum, which is just pretty much a mass on a string or a mass on a rod. If the rod is negligible, or if the mass of the rod is negligible, excuse me. So really, it's like a clock swinging back and forth. All right. So it asks us for how long is the pendulum, aka the length of the pendulum. So we know that the period is equal to 2 pi square root of the length of the pendulum divided by the acceleration due to gravity on Earth. Again, this function can change based on where you are. This particular problem is on Earth, so we'll just use G as 9.8. In that case, let's go ahead and just do the math real quick. To solve for L, let's go ahead and square both sides. Squaring the left side gives us t squared. Squaring the right side, 2 squared is 4, pi squared is just pi squared, and then squaring this radical here gets rid of it. So then we're just left with L over G. And then again, to solve for L, just do basic algebra, multiply both sides by G, and then divide both sides by 4 pi squared. That leaves us with this particular function. Here, we know everything already. We know T from the graph. T, again, we can extract from the graph, which is 4 seconds. G is 9.8, and then, again, pi is just a constant. So if we do that, plug and chug, we know that the length of the string will match choice C, which is 3.97 meters. Okay? Or, yeah. All right. Let's move on. Number 15, or quote unquote, the last question for this particular set. It says if the graph represent a 1 kilogram mass object on a spring, what is the spring constant? So there's a couple different ways to do this. The first thing that comes to my mind is the period function for a mass spring oscillation system. T is given as 2 pi radical m, where m represents the mass of the spring, or excuse me, the mass of the block, or mass of the ball, whatever is being oscillated, and then k is the spring constant. So to solve for k, we can just go ahead and again use the same strategy, square both sides, which makes t squared, and then 2 squared is 4, pi squared is pi squared, and then getting rid of the radical here by squaring it, which just leaves us with m over k. And then to solve for k, we just rearrange the function, move the k to the left side, move the t squared down to the right side. And then here we know the mass is 1, and we know the period is 4 seconds again from the graph. If we square it and we do the calculator work, you should get a value of 2.47 newtons per meter. And I want to point out here, newtons per meter is the common accepted unit for a spring constant. But if you want, just in case, it would be 2.47 kilograms per second squared, which is the same thing. Because if you think about it, Newton is force, and force is mass times acceleration. Therefore, the unit for mass is kilogram. The unit for acceleration is meters per second square. The meters in the acceleration unit will cancel with the meters down here in the denominator, and that'll leave you with just kilograms per second square. But again, newtons per meter is commonly accepted. Okay, I will just stick with that. All right. The other way to solve it is to set the spring force equal to the net force of a mass spring oscillation. Here, I've left out the negative sign for Hooke's law only because I'm finding K. And if I'm finding K, it doesn't really matter if it's positive or negative. The spring constant is a positive value, so putting the negative sign in front of it doesn't really do anything. So know when to leave the negative sign out, know when not to. In this case, I'm solving for K, which is just a positive constant, so I don't need to introduce a negative sign. You could if you want. Okay. All right. Here, you notice here I've replaced X with A because I know that if I use X as A, which is the amplitude, that'll generate a maximum acceleration because it's being stretched to the right most or compressed most to the left. And then from there, I can just do a quick substitution. Don't apply the strategy unless you're familiar with all your harmonics motion. The maximum acceleration is given as the amplitude times the angular frequency square. Okay, so if you know that, use the strategy. If you don't, stick with maybe the left function because it's pretty much straightforward. All right, from here, you notice that there's an A on both sides of the function. A on the left and A on the right will cancel out. And this leaves us with just K is equal to M mass times the angular frequency square. And mass in this particular problem is straightforward. It's just 1, which makes everything easy. And then the angular frequency we already found in quote unquote part question 10, the first question of the set is 1.57. And then we just got to make sure we square that sexy omega. Okay. And if you do all the calculator work, you will get the same value of 2.47 newtons per meter. All right. I hope that helps. Other than that, stay nerdy. Don't be whack.